Hello, hello. Welcome, welcome. Hopefully everyone is or can see me and hear me. Let me just get my screen sorted. Ta-da. Lovely. Hello, welcome. Hi, Edward. Nice to have you. I'm pretty sure you were here last time, weren't you? Welcome back. How are you doing? How's everybody doing? Please feel free to say hi in the chat. It's lovely to know who we've got here, and it's always nice to have faces back again or names back again. So that's great. If you're new, welcome. If you're not new, welcome back. Good. I'm glad you're doing well. I'm glad you're doing well. We've been doing these web classes for ages, so if you're an old, probably already know to download slides for today's session, which are in the description below. So please feel free to go and check those out and download them. Keep them, scribble all over them now, save a second copy, whatever works for you. But they are very, very useful in order to get yourself prepped, ready for exams. If you're mid-exams right now, then hopefully they're going really, really well. But if you're a year 12 student, or perhaps you're somebody just interested in understanding what A-level chemistry is like, then welcome. Please feel free to download the slides because you can use them for revision, etc., etc. We'll give it, oh, actually, no, we'll probably get started. Okay, let me get my screen sorted then, and then we can get started. So this is our A-level chemistry web class on mass spectrometry. Uh-oh. Well, you probably should go and do a bit of revision then, I'm guessing. If it were me, I'd make sure I was doing a bit of revision. So this is our A-level chemistry web class on mass spectrometry. Yeah, hopefully everybody does go, everything does go well tomorrow. I'm sure it will. I'm sure it will. So our objectives then are to understand how mass spectrometry works, to calculate relative masses from mass spectra, and to determine molecular structures from mass spectra as well. So hopefully, well, this might be new to some people, but it's more likely to be revision for some of us. So hopefully everybody goes, everybody's feeling nice and confident about it. We're not going to look at specific details of TOF or time of flight mass spectrometry because that is, I believe, only for AQA students. So we're not going to cover that specifically, but we are going to look at mass spec in general. And we're not going to look at the appearance of carbon-13 peaks, although I may mention it in the exam question. We'll see. Okay, so this is going to be about 50 minutes or so, and we'll try and whiz through as much of it as possible. We'll also try and have a go at some of our exam questions because they are very useful, but in some cases we may struggle to get through all of our questions. We'll do our best though, we'll do our best. Okay, so what do we already know? What do we already know? And for some reason, my what do I already know is here ahead of my specification points, but never mind. So what is relative atomic mass? Do we know what relative atomic mass is? Hi, Deeksha as well. Lovely to have you here. What is relative atomic mass? Do we know? There's a very nice, there is a definition that we should know off by heart because we have to be very specific with our understanding of relative atomic mass because there's loads of different ones. There's relative atomic mass, there's just molecular mass, there's formula mass, there's isotopic mass, there's molar mass. So all of these things are ever so slightly different. So we do need to know the differences between them. And specifically, absolutely brilliant. We've got some great answers in the comments. Very specifically, it is the mass of a carbon atom compared to 1/12 the mass of, sorry, a mass of an atom compared to 1/12 the mass of a carbon atom. Brilliant. And even yeah, lovely. It's also average. It's the average mass or mean mass of an atom compared to 1/12 the mass of carbon-12. Very nice. So relative atomic mass is the average mass of an atom, of an element, relative to 1/12, whoops, the mass of carbon 12, specifically carbon 12, because hopefully we do know that carbon can have multiple isotopes, including carbon 13. So it's specifically the carbon 12 atom. And it's 1/12 the mass of carbon 12, because at this point, when we determined relative atomic mass, we weren't 100% sure about protons existing. And because carbon is the most abundant element by mass, I believe, on Earth, and it's so important for us as carbon-based life forms, we base it around carbon, but it's not actually a carbon atom. It's at 1/12 of the mass of a carbon atom, which happens to be the mass of a proton or a neutron, approximately. An isotope then is what? What is an isotope? Isotope. Oh, that's really nice, Alyssa. Very good. Brilliant. That's a very succinct, very nice description. I'm not going to be able to write as much of that. I don't have very much space, but that's lovely. Really good. So the key thing, iso, I believe, means our different. So isotope, different structure, I think, is a very basic etymology of the word. So it's the same number of protons, but different numbers of neutrons. Really nice. So we know it's an atom of an element. I know it's carbon, for example, because it's got 6 protons, but it has a different number of neutrons. So it's a slightly heavier or slightly lighter atom of that element. Really nice. An atom of an element. So you can add in same number of protons. They will, in an exam, they will be for the same mark. So if you say it's an atom of a specific element, or if you say it's an atom with the same number of protons, they mean the same thing effectively. So they'd be for the same mark. An atom of an element with a different mass number. Whoops, too many S's. Mass number. Or again, for the same part of the mark or the same mark, you can say different numbers of neutrons. So isotopes have different numbers of neutrons to each other. Really lovely. If at any point you can't read my handwriting, I know it is a bit scrappy, especially when I try and write fast, then just let me know and I can try and write something again, or I can tell you what it's supposed to say, even if it doesn't look like it. And of course, if you have any questions, pop them in the chat and I'll do my best to answer them. If we speed through this content, we might even have some time at the end to ask generic chemistry questions as well if we need to. No worries, Dominic. Nice to have you here. Welcome. Okay, what's this term molecular mass then? And if you can, do you know the difference between molecular mass and relative atomic mass? So specifically, if we want the molecular mass, what are we looking for the mass of? Molecular mass is what? And how do we calculate it as well is a good thing. Molecular mass. Anyone know? Hi, Marianne, nice to have you. Hopefully you're doing well, ready for tomorrow. I'm sure you are. Yeah, lovely, Dominic. So molecular mass is the relative atomic masses in a molecule all added up. Yeah, brilliant. Lovely. So it's the sum of all of the relative atomic masses. Oops, can't spell. Relative atomic masses. It's the sum of all the relative atomic masses of all of the atoms in a molecule. I think my screen just went blank there, but hopefully it's back again. In a molecule. Lovely. So specifically, it's the mass of a molecule, one molecule of something. Okay, compared to relative atomic mass, which is just the mass of one atom, the average mass of one atom, taking into account all of the isotopes. Lovely. Let's keep going then. So for some reason, these are in an odd order. So usually we do the spec points first, but never mind. So if you're an AQA student, these are the specification points that we're going to be covering. If you're an Edexcel student, these are the specification points that we are looking at today. And then if you're an OCR student, these are the OCR spec points we're going to be covering. I say this every time, but I think it's so important. If you haven't already, download your specification and print it off and have it next to you, because it's such a good revision tool. Whenever you go to lessons, you can tick off, oh, I think we did that today, or oh, I didn't understand that, I'll need to revise that specifically, or whatever. So hopefully you can use your specifications as checklists basically for your revision in this. So useful. Oh, nice, Marianne, that's what we like to hear. Very good, well done, I'm impressed. Okay, so a little bit of mass spectrometry basics. Mass spectrometry is a method used to determine the mass of elements, isotopes, and molecules. So you can put almost anything into a mass spectrometer. Some molecules won't do so well in a mass spectrometer because they'll be too big. But you can put most things in and we can use it to work out, for example, what a mixture is made of. Maybe you've made a new substance and you've got no idea what it is. We use mass spectrometry in order to determine structure. It's a part of a chemical analysis. So we need to have some idea, and AQA students, you're going to need to know a little bit more detail than we're going to cover here. But we need to know the basic process that occurs in order to perform mass spectrometry. So step one is ionization. Briefly, what does that mean? Ionization, what's happening in the ionization section? So this is our ionization area. What happens? So basically, what is ionization? What does that mean? It's a phrase that hopefully we know, but what does it mean? Yeah, good. So ionization is the loss or gain of electrons. So in the ionization section, we turn them into positive ions. I believe there are some forms of mass spectrometry where you can add an electron, but the ones that we learn at A-level, and for the most part, you're absolutely right, we turn them into positive ions. We knock an electron off, at least one electron off, and we end up with a positively charged molecule or ion or isotope, and then it can enter into the rest of the spectrometer. Very nice. Okie dokie. So ionization, so one, like I say, or more, we can knock off more than one, but then you're getting quite unstable. One or more electrons is one or more electron is knocked off. Oops, a sample, leaving an ion with a positive charge. And obviously, if you knock off one electron, then as I think some people said, it's 1+ charge. You knock off 2 electrons, it's 2+ charge, etc. This is for A2 content, but what happens, what can be an issue, or sometimes it's useful, with knocking electrons off and destabilizing molecules? What can happen, therefore, in mass spectrometry, which is sometimes useful, sometimes not? If we've destabilized our molecules by knocking an electron off, if you've got a molecule, so it doesn't happen with elements or isotopes, but if you've got a molecule and you knock an electron off, so you destabilize it, what can happen to the molecule? What do we call it when they, yeah, lovely, Hallie, exactly right. We can get fragmentation occurs. So sometimes fragmentation occurs, just means it breaks up into smaller bits. And we'll look at that a little bit more later on. Okay, so now we've got our ions. It has to be an ion, otherwise it's not going to be accelerated through our electric fields. So it has to be a charged ion, otherwise it's not going to be accelerated. So then, because it's charged, it can be accelerated in our acceleration area. Oh no, sorry, I've gone back. There we go. It can be accelerated through our acceleration area. And so how does this occur? Oh, it's not letting me rub that out. That's useful. Okay, never mind. So the ions are attracted, yeah, very nice, Hallie. Very good. Attracted / accelerated. Accelerated. Oops, I didn't mean to write that. The ions, oh, I can't rub it out. That's annoying. Attracted or accelerated using a negative electric field. Opposites attract. And therefore you get, oh, we'll come to that in a second, Candy. Therefore you get an attraction. If you get an attraction, but they're traveling at a high speed, so they don't kind of veer off and stick to our negative plates. Oh, I forgot, I can't remember that. They are attracted and they go through a gap where they're attracted to another plate, which they go past, which they're attracted to another plate, they go past, and eventually they speed up so much that you get separation occurring. So the separation occurs where the heavier molecules take longer to travel through a straight mass spectrometer, or if you've got a curved one, then your heavier molecules will have a what are they called? A larger parabola. They will be travel on a larger curve, and the lighter molecules will travel on a shorter curve, and that's how you can therefore work out how big or small your molecules are. Or, like I say, if you've got a straight what they called flight path, then the lighter molecules will travel faster, the heavier molecules will travel slower because they're heavier, momentum, all that physicsy stuff, until they get detected at the detector. So the lighter, this is with a straight flight path, the lighter molecules travel, oh no, I can't remember about travel faster, so are detected first. And then also more highly charged ions as well will travel first because they will be higher, they'll have a greater attraction in the acceleration area. And how are they detected? How are ions detected in an ion detector? Does anybody know? Because they are charged particles, they actually can cause, yes, good, lovely. So they can gain an electron, which causes a flow of electrons, a movement of electrons, which is current. So they generate a current, or they cause current to occur. Really nice. So ions cause current on detector plates. Detector plates by gaining electrons. Really nice. Okay, anybody not happy with any of that, just let me know. Otherwise, let's have a quick look at doing some of our quote unquote more basic mass spectrometry application. So usually, especially if we're looking at AS and year 12, we only really focus on using mass spectrometry to look at our relative isotopic mass calculations. So initially, when we were first developing and discovering ions and so isotopes even, it was really, really useful to use mass spectrometry to determine approximate relative abundances of our atoms, or of our isotopes, sorry. It's still very, very useful, but we've kind of worked out what our relative abundances are by now. So it's actually more useful maybe doing analysis of chemical molecules. However, this is one of the things that we look at first when we think about mass spectrometry. So how do we do it? Does anybody know what the equation is? Can you remember? Have you recalled the equation maybe from GCSE? Because we do cover it not specifically using mass spectrometry, but we look at relative abundances and stuff at GCSE. Does anybody know how do we calculate the relative atomic mass of a sample if we've been given the relative abundance and the effective relative mass, or the mass to charge ratio? Anybody know? So our relative, oh, that's funny, relative atomic mass is calculated using what? Oh, lovely. Yeah, exactly right. Good. So it's the sum of, because we've got to add them all up, the sum of the relative abundance, which I'm going to call RA because I don't have much space. Actually, maybe I can just call it abundance. Abundance, yeah, times by their relative atomic, their mass to charge ratio, which we're assuming, especially A level, that the mass to charge ratio is 1 because only one electron would have been removed. So it's an ion of 1. So the mass to charge ratio is just their mass because it's the mass divided by 1. Having said that, they may sneak a sneaky question in, potentially, but it's unlikely. So abundance times the mass, which we take to be the mass to charge ratio. Sorry, yeah, that. And then we divide by 100. Why are we dividing by 100? Why are we dividing by 100? That looks great, Alyssa. Lovely. So let's just check. So 35 times 75%. Good, it's the sum of abundance. Because it's a percentage, it's out of 100, so we have to divide by 100. Really nice. That's useful to remember, just in case they give you a abundance that's not 100%. If they give you an abundance that's not as a percentage, then you'd need to divide by that amount. This is all to do with developing our math skills. Nice. So it's 35 times our 75% plus, I'm not going to put the percentage in actually, plus our 37, which is the mass of our other isotope, times 25%, divided by the total percentage, which is 100. And so chlorine should be, if we've got it right, should have a relative atomic mass of 35.5. If you get these questions in an exam, it is possible that they will give you a number which is ever so slightly different. Sorry, the answer will be a number which is ever so slightly different to the one you've got in your periodic table. So don't panic if it is, just double check your numbers and make sure you're happy that you've done all the calculations correctly. Because if they gave you a number, for example, 35.5, which is what's given in our periodic table, you could just quote that. And they would be obliged to give you at least 1 mark. So they may sneakily, or they may get you to quote it to, for example, 2 decimal places, in which case you need to make sure that you give it to the number of decimal places they've asked for. But it's always worth, and I'm sure you already do, checking with your periodic table. If you're calculating the relative atomic mass of chlorine and you get 70, you've probably done something wrong. If you're looking at calculating the relative atomic mass of bromine and you get 3, you've probably done something wrong, because it will be a number similar to the periodic table, but it may not be identical. Okay, how's everyone feeling? How confident are you feeling about all of that? So this is a way for me to understand how confident you guys are feeling, but also for you guys to assess yourselves. How confident are you? You can revise. Are you actually fine? You've got this sorted. Lovely. So you can give me a number, you can tell me, or you can give me a smiley face. It's entirely up to you, whichever you would prefer. Awesome. That looks good. Fair. And if you're halfway between the two, that's also absolutely fine. Lovely. Really nice. Fantastic. Okie dokie. Cool. Don't forget to ask questions if you do have them. But otherwise, we will keep pushing on. Okay, so this is an example question. This is a past paper question about mass spectrometry. So it says, the copper used to make a batch of coins is analysed by mass spectrometry. The mass spectrum is shown below. Blah, 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 blah. Calculate the relative atomic mass of the copper used to make the coins. Give your answer to 2 decimal places. So we basically got to do exactly the same thing. The one thing that I will do just to be sure, and you can assume that they aren't trying to trip you up, but I will just make sure that my percentages add up, because if they don't, there may have been a bit of information in the question that I've missed, telling me about a 3rd isotope or something like that. So because it only takes me half a second, I'm just going to check, do those numbers add up? Yes, they do. Great, that's fine. So I'm happy that I'm only using these values here. I haven't missed anything in the question. It's a nice quick check. So anybody got a value for me then? So we're calculating relative atomic mass. It's the same as we did before. It's the sum of the abundance times by what we're assuming is the exact mass divided by 100. That looks good. So don't forget to keep the numbers associated with each other. So 69.17% of the coins have a mass of 63. So I need to keep those numbers together. So 69.17 times 63 plus, and then I need to keep those numbers together, 30.83 times 65. And then I divide the whole thing by 100. Should give me 63.16, sorry, no, 6166. Or lovely. Well done to those of you that read/remembered. It says give your answer to 2 decimal places. And when I go to write something in on the answer line, I always go back and check. It's usually at the bottom of the question, so I always go back and check, have they asked for significant figures or decimal places, sorry. And it's usually at the bottom of the question, so it's usually fairly easy to find. In this case, yes, they've asked for 2 decimal places, so that would be 63.62. Well done, everybody. Fantastic. Next bit of the question says, bromine has 2 isotopes with relative atomic masses 79 and 81. Which of the following values for mass to charge ratio could correspond to a peak in the mass spectrum of bromine, Br2? You should assume that the ions detected have a single positive charge. So this is where maybe in some cases they can try to trick you, because if you've got a molecule or something, you can remove more, or anything, you can remove more than 1 electron. But here they specifically said you should assume the ions detected to have a single positive charge. So they've only had 1 electron removed. What are we thinking? Which of these following values for mass to charge ratio could correspond to a peak in the mass spectrum of bromine? So it's the mass divided by 1. That's what we've been told. It's got a charge of 1. So mass divided by 1. Does it equal 79.9 for bromine? Does it equal 80? Does it equal 159? Or does it equal 160? Anybody want to have a go? What do we think? A, B, C, or D? Bromine has 2 isotopes with relative isotopic masses of 79 and 81. So bromine can have a mass of 79, or it can have a mass of 81. Oh, nice. We have had some good. We've definitely had some thoughts. So it is, and they've even told you that it is Br2. Good. And therefore, very nice. We know that it's BR. So we just got to work out a quick bit of maths. What could it be? So our bromines could be 79, or they could be 81, or they could be one of each. So we can have 79 and a 79. We could have a 79 and an 81. We could have an 81 and a 79, or we could have an 81 and an 81. And so quick bit of maths should tell us what they add up to. So that's 158, or that would be 160, or 160, or 162. So our peak is definitely going to be 160. D. Well done, those of you that said D. Brilliant. Really nice. And they like these kind of questions because it really, especially as a multiple choice question, because it really means you have to think about what they're telling you, what the information is you've been given, and how to apply it. So very nice, very, very good. Well done. How are we doing for time? Not bad. Okay, so let's have a thinker then. This is kind of more year 13 content because it's more chemical analysis, but we should hopefully still be at the level where we can understand it and apply it and think about it. So let's have a go at some molecule identification. Okay, so relative molecular masses. We spoke briefly, and again, this is, I think, where we think about it more in year 13 or the full A level than year 12, but molecules can fragment during ionization. They can break apart. Now, they don't break apart and join back together randomly. They will only break apart by breaking a bond. So we can use a mass spectrum to find the molecular mass peak and some of the fragments. And if we can think about some of the fragments, we know what puts together. We know what makes up our molecule. So can anybody, and it's not so easy to see, but can anybody come up? No worries, Deeksha, have a lovely rest of your weekend. See you soon. Can anybody tell me any information they can get from this spectrum? What information can we glean from it? Can we work out what any of the peaks mean, what they represent? That's a good question, Naz. When do you know if it's an isotope of carbon or hydrogen? So let's have a think about what this end. Thank you, Mariam. We'll come to that in a second. That's really good. Let's have a think about what that peak means. So for OCR, you do have to be able to do fragmentation peaks, I believe. Yeah, I think so. Good, that's the molecular ion peak. Very nice, the MR or M plus peak, molecular ion peak. So that's the molecular ion peak. And if it's a molecular ion peak, we know that it represents the whole molecule, but with an electron removed. So just to come back to Naz's question about isotopes, this is, I said, oh, we may or may not mention it, so we're going to mention it. This tiny peak down here, which we can't really see, that tiny peak down there is due to the fact that something like 0.01%, I can never remember the actual number, of carbon atoms are carbon-13. So if you've got maybe one carbon in the whole of our sample that's carbon-13, then that molecule will have one more mass, a mass of one more than everything else. Carbon normally, if we look down here, carbon normally has a mass of 12. So if this is ethanol, it will have a mass of 12 times 2 carbons, plus 1 oxygen, plus 1, 2, 3, 6 hydrogens, gives us a total mass of 46. So normally our ethanol would have a peak of 46, but this tiny peak here is because one of the molecules maybe has a carbon-13 in it. So actually that one will have a peak molecular mass of 47. Let me know if that doesn't help. So when we look for our molecular ion peak, our M plus peak, so the plus, just to answer your question, Mr. AB, the plus because it's an ion, it's the molecular ion. It's an ion because it's had an electron removed, which means it has a positive charge. It's got one more proton, therefore, than it does electron. So it has an overall positive charge. So the M plus peak is telling us because it's a molecular ion, M plus molecular ion. Let me know if that doesn't help. Cool, good, lovely. So when we look for the molecular ion peak, you look for the most significant peak furthest to the right. So in this case, we have actually got a minuscule peak right over there to the right, just to the right of our M plus peak, but it's tiny. So that one can't be our molecular ion peak because it's not representing the whole molecule. It's only representing a tiny, tiny fraction of molecules. So the M plus peak is the most significant peak furthest to the right. So it might be second furthest to the right because of a carbon-13 peak, or it may be the furthest peak if we don't have or don't count that tiny, tiny carbon-13 peak. Good. So Gian, hopefully I've said your name right. Apologies if I haven't, but you're absolutely right. So the highest mass peak we've seen there is the molecular ion peak, and then the other ones are our fragments. So let's work out what some of these fragments are. So I'm going to skip on to the next one. So we've got our M plus peak. I'll just relabel that. We've got, we've got our, we sometimes call it M plus 1 or our carbon-13 peak as well. And then we mentioned some fragments. Brilliant, thank you. Then we mentioned some fragments. So Marianne, I think it was, said that our peak at 15, where is that? 1, 2, 3, 4, 5, here we go. So we've got a peak at 15, we've got a peak at 17, we've got a peak at 29, we've got a peak at 31. What do these masses represent? So a peak at 15 is going to be CH3, because one carbon has got a mass of 12 and 3 hydrogens have a mass of 3. So 15 is because of our CH3 fragment. So that could be perhaps when our structure has broken in that bond. If it has broken at that bond, we've got our CH3 bit, but we should also be able to find peaks that represent the rest of the molecule. So let's use my colors. I love a bit of color. Let's just go orange. Let's use my colors here. So we've got that one, peak 15, which is due to our CH3 fragment. If we've got our CH3 fragment, yeah, lovely. Looks like some people have recognized the other bit, which I'm going to do in blue, because if it's broken, you've got to have one, you've got to have both bits. You can't just randomly only have one bit and not the other. So you've got to have both bits. So the other bit would be a peak at 12, 13, 14, 15, 31. So I'll put that on there. Is our CH2OH peak. And it's positively charged because the whole molecule will be positively charged and it's broken off. So we can label it as being positively charged. So that's our peak at 31. Yeah, lovely, really nice. So we've recognized that OH is likely to be our one at 17. Because if we've broken that bond there, we've just snatched the OH off. So we've got our OH peak, and that means we should also see the rest of the molecule as well. So hopefully that will work out nicely. So that's our OH bit. Good, really nice. It looks like other people have recognized that as well. And we're absolutely right. That means if we've snapped it at that point, then the rest of the molecule must be or is our peak at 29. So our molecule doesn't fragment, this molecule doesn't fragment in many other ways apart from those ones we've recognized here. And you will notice as well that you get the two halves of the peaks if it snaps in half. Notice that our peak at 31 is quite abundant, so that's likely to be perhaps the other bits have broken down a little bit or have fragmented further. What am I doing? 29, that one, which is CH2CH3. That one as well, and then we know we've got iron plus peak as well. It's really useful to use fragmentation patterns when you're trying to determine structures of molecules, because as you can see here we have got a molecule which also has an MR of 46. Why do we know, and how can we be sure, if you were given this in an exam question, how would you prove or how would you explain that this spectrum is definitely of ethanol and not of this other molecule, this ether? What would you be looking out for, perhaps, do you think, if you thought this might be a structure of an ether? I'm going to go for purple. Lovely, Mr. AB. Why would you have a 33? What would the 33 be? So AQA I feel like we do have to do fragmentation, but not until A2. Because I've definitely taught it on the AQA specification. Yeah, Naz agrees. Okay, cool. It's not just me. Yeah, lovely. Well done. So this bit, this fragment at 16, 28, 29, 30, 31. Hold on, let me check my calculation because I don't trust my mental arithmetic. 31. So there may also be a peak at 31. Oh, you learned it in AS. Okay, fair enough. It might be in AS as well. Something in my head told me that it's kind of when you go back to it, the A2, but that could have just been the way that we taught it, because we taught it as a full 2-year thing. So that could have just been the way that we taught it. But good. So there is a peak at 17. There is a peak at 31. So that one would be our peak at 15. That one will be a peak at 31. However, there's no way to get a peak of 29, which is definitely present. And there's no way, as you say, to get a peak of 17, which is definitely present. So we know that this spectra shows ethanol, not this ether, because we've got peaks at 17 and 29, which corresponds to fragments of ethanol, and they are not present. Those fragments cannot be present or aren't present in our ether. What's the functional group on an ether? The functional group is the carbon, single bond oxygen, single bond carbon. That's the ether functional group. You may have met it once or twice. It's one of those functional groups which you perhaps maybe mention in passing sometimes, or you know of because we know that, we know that it's an isomer. Sometimes it can be used in isomer questions, drawing structural isomers or functional group isomers. You may have met it because dry ether is a solvent that's used when we can't have water present. So you may have heard it then, but it's one of those functional groups which we touch on a tiny bit because it rarely comes up. It's good to kind of recognize that it can exist, but I wouldn't worry too much about it apart from that. Cool. Let's just put that as an ether. There we go. Yeah, exactly. Good. Okay, right. Let's whiz on. Well done, everybody. So let me know how confident you're feeling, and then we'll have a go through some of our exam questions. We may have time for all of them, but I am going to have to disappear just before the hour, just before 6 for another lesson. Do I have any predictions for tomorrow? I would hate to predict because they're all so different for different specifications. There are loads of topics that come up, in different exam boards in their specific papers almost every year. And although it's not every year, it is almost every year. So if you look back through a couple of past papers, you'll find that there are very repetitive questions. So I would assume that they would be very repetitive again, but I don't know either way, to be honest. Your exam on Tuesday? I thought they're all tomorrow. Yeah, something like that would be nice. So they like to have, obviously, I'm sure there'll be something on pH, for example, but what form it will take, we don't know. OCRA, okay, fair enough. Cool, lovely, thanks guys. Okay, let's have a go at these exam questions then and see if we can whiz them in the next 10 minutes. So, which of the following values for the mass to charge ratio for singly charged ions would be present in the mass spectrum of propanol, CH3, CH2, CHO, but not of propanone, CH3, CO, CH3? It might be that is one of you maybe doing AS and the other doing A2, perhaps. Yeah, double check exam timetables, guys, and make sure that you look at your date. But I'm sure you're all right. Just make sure you double check, just in cases. Okay, anyone got any thoughts about this one? So which of the following values for mass to charge ratio, i.e. the mass, for a singly charged ion, i.e. the mass, would be present in the mass spectrum of propanol, but not in propanone? Okay, there we go. That might be why. Worth checking. Oh, you did the opposite. Okay, no worries, that's fine. Okay, we reckon B. Why do we reckon B? Absolutely correct, it is B, but why? If I draw them out, it might be easier. So CH3, CH2, C. So propanaldehyde is the carboxylic acid functional group at the end of the chain, including the hydrogen. Nice, that looks good, Josh. And whereas propanone is a ketone, so the carbonyl group needs to be in the middle of the molecule. CH3, C, double bond O, C, CH3. So we're looking at which functional groups will be present in propanal, but not in propanone. So the CH3 will be, so we can ignore A because that will be present in both. And so will it, however, the 29, the double is not a nice way of describing it, both of the carbons in the same functional group, in the same fragment, would not be present in the ketone, but will be present in the aldehyde. So it would be that one. Very good, well done. Lovely. What about the second question on this page? Let me know if anyone's not happy, by the way, with any of that. With that. What about the second question, though? So two ketones both have an MR of 86. Which peak due to fragmentation into singly charged ions, so we only need to worry about one, would you expect to be present in the mass spectrum of one but not the other? Again, I'm just going to draw them out because I find it helps. So with this one, we've got our CH3, then our C double bond O, then CH2, CH2, then CH3. Speed hydrogens. Or we've got CH3, CH2, then C double bond O, then CH2, CH3. So we've got to work out where might they fragment, which produces different speed hydrogens again. Fragments. Looks promising. So again, what fragment is that representing? It is C. What fragment is that representing? Yeah, nice. Good. So that section is not possible. You can't, we can get, so that's this one. We can get CH2, CH3 in both of them. We can get CH on its own in both of them. Either end. But what we can't get is the fragment that is CH3, C double bond O. So very nice, well done. Awesome. Okay, how are we doing for time? Oh, okay. We'll just do these questions and then we might have to disappear. Okay, so it says it is necessary to use several analytical techniques to determine the structure of an unknown compound. An analytical chemist was asked to determine the structure of compound Q, which was found in a waste tank in a mixture of volatile liquids. Compound Q has the molecular formula C4H7Cl. Just in case you can't read the small writing. It's a volatile liquid which does not produce misty fumes when added to water. Suggest how a chemist could obtain a sample of Q for analysis from the mixture of volatile liquids. And then identify the bond that causes the major absorption at that peak. Before we answer those questions, I'm just going to say, why is it added? It does not produce misty fumes when added to water. Why has that been included in the question? What is that telling us? Or what can we get from that as a piece of information in our exam question? Does anyone know? So not that it doesn't react with HCl, but it doesn't produce HCl. That's the one, yeah. It doesn't produce HCl when added to water. Very good, well done. which means it's not which structure. It's not what kind of compound. Does anybody know? One of the, I think, more interesting, more exciting functional groups that we learn about at A-level chemistry, one of them is particularly good at producing HCl, which is our misty fumes, when added to water. And that is, well done, really nice, our acyl chloride. So we know that it is not an acyl chloride. Now, this may not be useful to us because we're not going to go on to do the rest of this question, but I think it's very important to pick up on these clues in exam questions. Always really useful. So we know this isn't an acyl chloride. And just a reminder, in case you're not confident, an acyl chloride is the one that looks like a carboxylic acid or an aldehyde, but it's got a chlorine on it as our additional group. Lovely. Cool. Okay, let's just answer these A and B, and then I'm going to have to disappear. So suggest how the chemist could obtain a sample of Q for analysis from the mixture of volatile liquids. How do we separate out samples from the mixture of volatile liquids? What do we reckon? Yeah. Can you be more specific, Hallie? What separating technique are you describing? Yeah, good, lovely. So distillation or fractional distillation, good, is one of our examples. You only actually need to say distillation, but fractional distillation if you want to. Lovely, well done. Or you can say gas liquid chromatography, GLC, which is technically a separation technique. So you can use gas liquid chromatography, but oops, I've spelled distillation totally wrong. Distillation, there we go. But I think distillation is kind of the easier / more useful answer. Lovely. And then this final question that we'll do today is the infrared spectrum of Q contains a major absorption at 1724 centimeters to the -1. Identify the bond which causes this absorption. Even if we're not sure, we can take a stab because there's only really 3 bonds that you need to be aware of majorly when you're doing IR spectroscopy. Yeah, good. And it's nearly always going to be a C double bond O. Yeah, good. And actually, if you have your data sheet in front of you, you'll notice that is it. That is the correct one. So well done. But if you had to guess, it's either going to be a C single bond O, or it's going to be a C double bond O, or it's going to be a C double bond C. Those are only really the peaks that they're ever going to ask you to identify in IR. You may be asked to identify other ones, but those are the main ones. So even if you aren't sure, you're running out of time, whack one of those down. But really nice. In this case, it is C double bond O. Awesome. Okay, apologies, we haven't managed to have a go at that exam question, but I'm going to need to disappear off, so we're not going to have time. Lovely, thank you, Marianne. That's brilliant. So hopefully we have a basic understanding of how mass spectrometry works. If you're AQA, you may need to go and look in a little bit more detail at, for example, the different types of ionization techniques and applying it in exam questions. We hopefully are all confident at calculating relative masses using mass spectra. So rather than just giving the data, taking it from a spectrum and then calculating it. And hopefully we are confident with determining molecular structures from mass spectra. So looking at those fragmentation patterns, thinking about what our molecular ion peak is telling us, etc. Fantastic. Right, I'm going to have to disappear, so apologies we didn't have any time for extra questions, but hopefully I'll see you at a future web class. Keep an eye on our timetable to see when we've got web classes coming up. It's been awesome having you here and being so engaging and interactive. That is fabulous. Yes, really good luck to everybody who's got their A-levels exams, who are mid-exams at the moment, or who've got their exams coming up soon. I've got everything crossed for you. Just make sure you sleep well the night before. And stay hydrated, and you can only do your best, and I'm sure your best will be brilliant. So really well done. Fantastic, guys. I will see you hopefully very soon. Have a lovely rest of your week and rest of your exam period, and yeah, see you soon. Thank you, guys. Well done.